All right, thanks. Good morning, everyone. So the context for this work is work done by our esteemed session chair and others, Shallow, Schwartz, and Lineal. Beautiful sequence of works that gave new hardness results for evidence of hardness of pack learning for problems that we previously had no hardness results for, such as improper pack learning of things like DNFs. Previously, hardness of improper pack learning had typically been based on cryptographic hardness assumptions, and these had not succeeded in giving such hardness results. And one of the major novelties in the works of Danieli et al. Were to use a new type of hardness assumption, specifically use an assumption about hardness of refuting random constraint satisfaction problems, in particular refutation of random k-sat, which is a big topic of study in the world of constraint satisfaction problems and refutation, and a very natural conjecture based on the best known algorithms. And so the point of the work that I'll be talking about was to try to better understand and clarify what exactly is the relationship between refutation and pack learning, and kind of deconstruct the work of Danieli et al. And what we found through this effort is identifying a form of refutation, which I call random right-hand side refutation, RRHS refutability, that is actually equivalent to pack learning. I should say this throughout I'm talking about the distribution-free model of pack learning. So specifically, having efficient, say, polynomial time pack learning for some concept class P is equivalent to having polynomial time random right-hand side refutability of a related concept class, which is dual to the class P in a sense that I'll talk about. Okay, so I will define more precisely what is random right-hand side refutability and what is the notion of duality between two concept classes that comes up here. All right, and so one consequence of this is pack learning of DNF is, again, improper learning in the distribution-free model is polynomially equivalent to random right-hand side refutability of DNF. Okay, so it turns out that for DNF formulas, and this is implicit in the work of Danieli et al., that for DNF formulas are self-dual or equivalent to their dual. And so we get an equivalence of these two tasks for DNF formulas. And another benefit of this equivalence is that for this notion of refutability, it holds for all time bounds, from polynomial all the way up to exponential. And our best known algorithms for pack learning DNF are exponential, like 2 to the cube root of n. Whereas the relationship to refuting random constraint satisfaction problems in the work of Danieli et al. Is limited up to quasi-polynomial hardness because the methods break once the sample complexity exceeds quasi-polynomial. Okay, so let me just use the few minutes I have to explain what is this notion of random right-hand side refutability. I'll start with just a kind of general discussion of what is a refutation algorithm. So I have some class Q of predicates. Is there a pointer here? Yeah. I have some class Q of predicates, and what a refuter for this class is an algorithm, a randomized, efficient algorithm, that can prove unsatisfiability of a system of equations where the constraints, the left-hand sides of the equations, are coming from the class Q. Okay, and now the right-hand sides, we allow them to be bits, so you may be asking that some of the constraints are true and some are false. And the question is, all right, so clearly for most interesting classes of predicates, deciding in the worst case whether such a system is satisfiable or not is NP hard. And so what a refuter tries to do is not necessarily solve this on most instances, on all instances, but rather on many instances be able to prove unsatisfiability. All right, and so what do we require? So for such a algorithm so we think of this algorithm as outputting 1 when it thinks that the system is unsatisfiable, and so for that to be convincing, if the system is satisfiable, the algorithm should always say 1 with small probability. And this is just over the coin tosses of the algorithm, so this is just a worst case condition on satisfiable instances. And then the completeness is more of an average case condition, so we don't, again, require that it always succeeds in proving unsatisfiability, but for many unsatisfiable instances, the algorithm should declare unsatisfiable. Okay. Now, that's just general refutation. Now, when people study refutation of, say, random constraint satisfaction problems like KSAT, there, the constraints are like, for example, K-clauses, disjunctions of K-literals. The right-hand sides are always 1, so like in a KSAT problem, you're asking that all the clauses are true. That's what it means for it to be satisfiable. And when people talk about refuting random KSAT, the clauses are chosen at random. So, and people study how many random clauses do I need to be able to efficiently prove the unsatisfiability of a system of a KSAT instance. In random right-hand side refutability, the difference is now, so our constraints come from this class Q, but we require that we can prove unsatisfiability in the worst case over all choices of the functions q1 to qn, and the only thing that's random are the right-hand sides, whether we're asking the constraints to be, the equations to be true or false. Okay, so it's kind of like a semi-random instance of constraint satisfaction. Worst case left-hand sides, random right-hand sides. Okay. The other thing which I need to define to make sense of the result is what is this notion of duality of concept classes. It's very simple. It's just where so I have one concept class that's described by string, the functions are described by strings x, and their inputs are y, and the dual class is obtained where I switch the role of x and y. I think of y describing the function and x as the input. Okay, and so some natural things like parity functions, thinking of x as describing a parity of y is the same as thinking of y as describing a parity of x, are self-dual. And as I mentioned, implicit in the work of Danieli et al., for DNF formulas, it is not self-dual, but it's equivalent to its dual through a standard notion of pack reduction. I can map formulas to bigger assignments and assignments to bigger formulas, polynomially larger, where I switch the role of assignment and formula, and I get the same value. Okay, and so that makes sense of this theorem, so again, yeah, if efficient pack learning of any concept class is equivalent to this efficient random right-hand side refutability. I won't say much about the proof because of the short time. You can come to my poster yesterday if you can go backwards in time or look at the paper. One direction, again, is implicit in the work of Danieli et al., showing that if you can learn, then you can solve these kind of refutation problems. And the other direction is is new. It's using ideas from theory of pseudo-randomness in a somewhat non-standard setting, along with boosting to prove the other direction. But rather, I'd just like to mention a couple of directions for future work. So, as I said, one of the benefits of this form of refutation of this result is that it holds even up to the level of exponential hardness, but people have not really studied this random right-hand side refutability of DNFs in the world of refutation algorithms. So can we get an exponential hardness for learning DNF based on something that people are actually studying in refutation? Another, on the more positive side, is can we use existing work in refutation to design new learning algorithms or vice versa? And what actually started me on this was a speculative hope that new techniques for proving hardness of learning might also be useful for some new hardness results in differential privacy. So far, I haven't seen how to make that work, but maybe it's possible. And then I'd also like to mention there is some independent work, unpublished manuscript of Pravesh Kotari and Roy Livni, giving a similar equivalence, but not for pack learning, but between agnostic learning and a corresponding variant of random right-hand side refutability. And one nice thing about their equivalence is that it holds even for distribution-specific learning, and the reason for that is that in the agnostic setting, you can do boosting even in a distribution-specific setting. I'll stop there.
Questions?
Along the line of your second bullet, do existing refutation algorithms, if we sort of translate them, correspond to sort of typical things people look at in learning, or do they like suggest some other kind of thing to do?
Yeah, so I'm an expert neither on learning nor on refutation, right? And I'm a complexity and hardness person, and that's what kind of looking to use this to get positive results is sort of new territory for someone like me. I've looked a bit. There is work on refutation of semi-random constraint satisfaction, a paper of Feige. When you translate it to learning problems, it's not the most natural learning problems that you get out, but maybe one can massage it to start to get results for some more things that would be of interest to the learning world.
More questions? If not, so let's thank Salil again.